Welcome to lecture 1 of your course on classical mechanics. This lecture is going to introduce the notion of motion, and specifically we're going to talk about the difference between kinematics and dynamics, and that is primarily a terminology thing. I'm going to talk about what do you mean by motion in the first place. Am I moving right now? In what sense am I not? We talk about what's called frames of reference and coordinate system. That'll be very important as a kind of foundation of describing everything we do down the line. And then we'll introduce the concept of displacement, and not just that, we'll also introduce it when we're dealing with situations that require more than one dimension. And we'll talk about what that all means in just a second. So let's get started. So these two terms, kinematics and dynamics, together they form what we might call mechanics, specifically classical mechanics. I'll talk about what's classical about it in a second. Kinematics is a term, it comes from the Greek kinema, which means motion. And dynamics comes from the Greek dynamis, which means power or strength. And it sort of gives you an idea what they mean. Kinematics in physics is the term that we use to describe that we give to a description of motion. This here is a description of motion. So this is what quantities do we use to talk about things moving, to describe them accurately. How are those different quantities related? Dynamics, at least in the way that the term is used in physics, refers to, roughly speaking, explanations of motion. Why does stuff move? What are the underlying laws to determine how things move? In a sense, this is mostly mathematics. We're defining some quantities, and we worry about the connections between them, but there are no sort of physical hypotheses here. 1 + 1 is 2. Well, nature can't make that wrong, but gravity could work differently in nature, for example. And we'll see how that plays out. In our case, altogether, we are studying what's called classical mechanics. So mechanics is just those two concepts together, kinematics, dynamics, classical mechanics. And classical is really just kind of a funny word in physics. It really means things that is not. Classical means it's not too small. So the objects we're dealing with, they're not too small, so they're not atoms. Atoms, this isn't a good description of how atoms work. It's not too big. It doesn't really work on the scale of galaxies either. You can tell that there's a big range of stuff in between. Anything from bugs to people to cars to planets, right? Classical mechanics is a good description. But not only that, it also means that it's not too fast. I'm just going to put here roughly speed of light. So things that go too fast, get close to the speed of light, those again would behave in ways that don't act classically. Right? So just using this term. We're not going to worry about it because we're not going to worry about the sort of extremes. Actually, we'll go a little bit in this course, but kind of to probe the edge of the regime in which classical mechanics holds. Alright, so that's just terminology so far. Now let's think about the concepts in some more detail. So let's imagine the following situation. Let's imagine I'm sitting on a bus. It's me, your instructor, sitting on a bus. The bus is zooming down the highway. Am I moving? Well, it depends, right? The answer is it depends. In what sense am I moving? Well, certainly pieces of me might be moving. I might be moving my hand, I might be moving my head, I might be stretching my legs, but that's not what I'm going to worry about. Right? I can think of myself as a single object that's in a single place. We call that idea the particle model, describing motion, where we sort of say, yes, it's an extended object, I've got fingers, I've got feet, they're in different places, but really I can think of myself as, to a good approximation, being in the same spot. Right. So that's our assumption. But in that sense, I'm in a single spot right here. Am I moving? Well, you might say, no, I'm sitting in the same seat the whole time. So that would be one answer. No. Just sitting in the same seat. But then again, my seat, the seat I'm in, is part of the bus, and the bus is going down the highway. So the answer might be yes. At 70 miles per hour down the highway. Those are the only two answers I could give. Well, maybe not. Let me zoom out a bit of this picture. We're going to zoom out really far, and then I might look at the Earth right here. This is the Earth. Here's the equator, right? And my bus is driving somewhere here. You can barely see it. Right? It's driving along around the Earth, but the Earth is spinning because the Earth. That's what the Earth does. That's why we have day and night. The Earth is spinning. So, you know, that makes it move. But not only that, the Earth is also going in a big giant circle around the Sun, if I zoom out further. And then I might say something like, yes, at 30 kilometers per second around the Sun. Right, because the Earth as a whole is traveling in its orbit around the Sun. And if you do the math, or if you look it up, it's about 30 kilometers a second, or a little bit under 20 miles per second. So this is very fast. So how fast am I moving? Well, it could be 0. Your answer could be 0. Your answer could be 70 miles per hour. Your answer could be 30 kilometers per second. Or maybe we should zoom out even further and go all crazy and say, yes, at 200-ish kilometers per second around the galaxy. Because if I look at my solar system, our solar system, and I zoom out really even further, so here, if I try to draw the galaxy here for a second, right, this is the galaxy with its spiral arms. We are living somewhere here. This is roughly where our solar system is. It's sort of in the suburbs of the galaxy, if you like. We're going around the galaxy at around 200 kilometers per second. So which of these answers is correct? Which of these answers says, yes, I am moving, or no, I'm not moving, and how fast? Of course, none of them is more correct than any others. They're all correct, but it depends on what's called your frame of reference. Let's write this down. The answer is, it depends on your frame of reference. That's another term we're going to need lots. So let's be a bit more specific about what we mean by that. So by a frame of reference, we tend to mean a collection of the following things. First thing we need to define a frame of reference is a notion of rest. It's not motion and notion, but an idea of rest. So I need some kind of reference point that is at rest. So e.g., relative to the bus, I am at rest. So the relative to the bus, this defines my notion of rest, right? The bus is assumed to be at rest. The bus, I'm not changing a position relative to the bus. So, or I could say relative to the road, or the trees by the side of the road, I am going 70 miles per hour, right? So relative to the road, relative to the bus, that's what defines my notion of rest. I say the road is at rest. If the road is at rest, then I'm going 70. If the bus is at rest, I'm going 0. Because the bus is moving relative to the road, but I can still define my notion of rest relative to the bus. I mean, the road is not at rest either. It's on the earth relative to the sun. The earth is moving around the sun. I am going, 30 kilometers per second. Right, and then you can think the center of the galaxy would be another one. So those define my notion of rest. That's the first thing we need to have a frame of reference. The second thing that we include in this concept is an actual way to measure position. And a change in position is ultimately what motion boils down to. Am I changing my position? To precisely express or measure positions of objects, of me, the bus, so on. The way we do this is via what's called a coordinate system. So a coordinate system is a way, you can think of it as imagining you have a really long ruler, and you put the ruler down on the road, or in your lab, or on your table, right? Whatever your situation. You have a long ruler, and you're saying, okay, where am I putting down my ruler? Right? So you can put down a ruler in some place, and that decides where's the 0 point. The 0 point is where the ruler starts. And then you can point the ruler in different directions, and allows you to measure different position in different directions. Well, that ruler acts as what we call a coordinate axis. So a coordinate system includes these notions. It includes an origin. Again, there's a lot of terminology right now. So this is the 0 position. The place where we say, okay, this position here is 0. If I want to measure where I am, I need to say I'm 50 feet. That doesn't mean anything, right? You've got to tell me 50 feet from where. What's your reference point? What's your origin? Of 50 feet from the lamppost, and then in what direction? North, south, east, west, maybe above or below, or some combination of them. The origin. I need coordinate axes. One or more, right? So I might measure distance north, south, east, west, and up and down. 3 dimensions, let's say. Coordinate axes. So these really define directions. And using north, south, for example, that is itself a way of doing that. Define directions. And we'll see all of it in practice. So if this is very abstract right now, don't worry, it'll soon make sense. And then we also need some kind of scale or units, right? How am I measuring? I am at 50 east of the lamppost. Well, 50 what? 50 meters, 50 miles, 50 inches. You know, what is my scale, and what is my unit of length? All right, and having those, so I've got a notion of rest, right? What does it mean to be at rest? It allows me to talk about, how 30 kilometers for the 70 miles per hour. And then I have a coordinate system, a way to measure precisely positions of objects and express in words and numbers where exactly an object is. Right? So this helps us to be precise about it when you want to describe the position and therefore subsequently the motion of objects. Now those axes, those rulers, right? You can imagine them as essentially rulers that we put down on the ground, one or more, or stick in the air somehow, we imagine them to be infinitely long. So they don't stop. Coordinate systems don't stop. They're infinitely long, and they also have negative numbers, right? So you could go, if you put down your ruler on the ground. So here's a, let's imagine here's a little tree, and I'm going to put down my ruler. So it starts at a tree and goes this way, right? So 1 meter, 2 meters, 3 meters, 4 meters maybe. Well, I could be at this position here. That might then be minus 3 meters, or it could be the position here, maybe plus 8 meters, for example. So those are all options. We imagine our rulers to just extend infinitely in all directions. Let's look at that in action. Let's imagine the following situation. Here's my front door right here, and then there's a flower over here, somewhere 3 meters from my front door. Then along the same line, so along a single line, there's a tree over here, 2 meters, of course not drawn to scale. And then on the other side, all in one long line, there's my car. It's 6 meters from the front door of the house. So everything is along one long line, and you've got the distances there. Now I might ask, where is the flower? Now, of course, you might just say it's 3 meters from the front door, to the left, or the way we're looking at it. But let's do it in terms of a coordinate system. Now, what's our notion of rest? Probably we say the house and the flower and the tree, they're at rest, right? We don't care about zooming through the universe on a tiny planet right now. That's beside the point, right? More often than not, from the context, it's entirely clear what the notion of rest is. But we need to define a coordinate system. So let me do this like this. One way to draw those is just, I'm going to make a little line where my origin is here. I could draw a little dot. And then I want to have a direction that tells me which way am I measuring numbers as positive. So if I imagine I have a ruler, I put my 0 point of my ruler here, and then I have it point to the right. In that case, I might say the position of the flower let me give it a symbol. Often we like to use the letter X for positions. I'm not sure why, it just sort of stuck. Let me call this X1 because this is my coordinate system 1. I want to show you different coordinate system choices in a minute. X1, well, if you imagine you put the ruler here and you look along it, well, the flower is going to be where the ruler has its 2 meter mark. So X1 would be 2.0 meters, 2 meters. It depends on your precision, right? Is it 2.0000? Depends on context, right? How precise you can be. That'll be one way to say what a flower is. You have to tell me what's your coordinate system. Oh, it's at the tree pointing towards the flower and house and the car. Okay, you're at 2 meters. The other choices we could have made. For example, we could start at a house and say this is my coordinate system. And I'm going to have my coordinate system point this way. Let this be my second coordinate system choice. In that case, the position of the flower we call it X2. We put a circle around it. That's what I did up there. Well, let's have a look. I'm going to put my ruler here, and it's pointing this way, so it's going to have the 1 meter, 2 meter, 3 meter mark right here. It doesn't matter whether an actual ruler would be 3 meters long. It's not the point, right? I can imagine my ruler to be infinitely long, while the flower will be at the 3 meter mark, provided I have my 0 point, my origin, right here, right? So this would be my origin. And in the case of the blue coordinate system, number 1, this would be my origin here. The tree is the origin, the house is the origin. And so I put 3.0 meters here. Can we make other choices? Sure, there's lots of them. I'm probably going to run out of colors before I run out of coordinate system choices. How about we start at the same spot here, but I'm going to have my ruler point this way now. Make this number 3. So it's the same origin as number 2, but my ruler points a different way. So I've changed the direction, right? Remember from before, a coordinate system involves an origin, a coordinate system and coordinate axes, and a unit. Units has been meters this whole time. It's kind of the boring one. We're not going to change it. 2 and 3 have the same origin, but different coordinate axes in different direction. In that case, I'm just going to write it like this. We're going to get, well, this will be 1 meter, 2 meters, 3 meters, 4 meters. Okay, we're never going to get to a flower because the flower's on the other side. We'd have to go backwards. So you get -1, -2, -3 meters. And none of them is more right than the others. Right? They're all just different choices. Of course, I could also pick the car. I'm going to let's just do one more, I guess. So I'll take this one, cars, my origin, and let me have my axis point to the right. This is going to be number 4. Well, the position of the flower in coordinate system number 4 would be, we can just look at this. This is a total of 3 plus 6. That's 9 meters to the left of the car, but the coordinate axis points to the right. So we're going to be at a position minus 9.0 meters. Now the important part is when picking a coordinate system, it's not that one is more right than the others, but depending what you're trying to do, what sort of problem you're trying to solve, what type of situation you're trying to think about, there tend to be coordinate systems that are easier to use than others. For example, I could have picked my favorite store downtown that's 3 miles this way as my origin, but then I just have really big numbers because everything would be happening at 5 minus 5,000 meters minus 5,002 meters. It's just kind of annoying to deal with big numbers, I suppose, right? So we tend to pick sensible coordinate systems, like an origin, maybe where we start, or where we end, or what's kind of the edge of, what's the relevant area that we're analyzing, right? But technically speaking, any choice is going to work. Another interesting coordinate system we could have chosen the flower as our origin. Nothing wrong with that. In that case, the position of the flower would just have been x equals 0, because it is right at the origin. So if I want to convert from one coordinate system to the other, I essentially just have to play with minus signs and adding and subtracting numbers. For example, if I want to know the position of the car in the purple one, would be +6. But in the blue one, it would be at +11 meters, because 2 plus 3 plus 6 is 11. Right, the position of the car. And for any object, if I want to go from blue to purple, essentially subtract 5 meters. So it's kind of easy to convert between them. So once you've got one, in a sense, you have them all. It's really just a matter of choice. How do you describe the situation? The physical setup is exactly the same, just different way of describing the same thing. We're going to continue looking at this situation, but I now want to introduce a new concept, that's displacement. So we talked about position. Position was where is an object. Right? Displacement is very similar, but it really denotes a change of position. Let's write this down. Displacement means change in position. It's something I can express in a coordinate system. For displacement is change in position, we tend to use the symbol delta x, or later delta y, delta z, but this capital triangle is a Greek capital letter delta, that's the Greek D sound if you were to read Greek. And in physics and math, it's often used to denote a sort of difference in something. So the delta x, that's like one symbol, like one concept, it denotes a difference in position if the variable we've used to describe position is x, which is what we did just now. So an example is, I walk from my front door to the car. What's my displacement? Well, the way I'd figure it out is I ask where do I start and where do I end. To do that I need a coordinate system, right? So I might say in coordinate system 1, I might say x start would be, well, it's gonna, this is the origin, so this is at, it's 5 meters, so it start at 5 meters. I end at the car, right, going to the car, so that's 2 plus 3 plus 6 in the same direction that the axis is pointing to the right. That's the plus, it's 11 meters. So my change in x is, well, where do I end up minus where do I start during the time interval that I'm looking at, right? I don't care what happens afterwards or before. I'm just worried about the delta x during this process where I start here and end here. So I can plug those values in. 11 minus 5 comes to 6.0 meters. Now, of course, I could describe the same thing in other coordinate system. Let me do number 3 first. So 3 first, I start at my house. In this case, my starting position would be 0 meters because I start at the origin, right? For coordinate system 3, the house, the front door is the origin. And then I end. Well, where do I end? At the car. That is, if I imagine my long ruler on the ground, this would be parked at position 6 meters. And so that implies, so this sort of double arrow, right? That is math for what's just come before implies that. So delta x, the change in position, x end minus x start is equal to, well, 6 minus 0, that's just 6. Alright, let's do the mole, I suppose. So let me go to coordinate system number 4. I'm going to describe this situation, coordinate system number 4. I'll have to move the sheet up and down, but hopefully you've got this picture in the notes now. Coordinate system 4, I start, well, where do I start? In coordinate system 4, the house is 6 meters from the origin, but the positive direction is right, so it's 6 meters in the negative direction, right? We'd have to extend the ruler sort of beyond its 0 point into the negatives. So it would start at, what am I doing? Sorry. Minus 6 meters, and then we end at 0 meters, because we end at the origin, right? The car is the origin in this coordinate system. Notice origin does not mean where do I start, where does something begin. It is a term referring to my choice of describing positions, right, as part of the coordinate system. So if I use this one, I'm going to get delta x is x end minus x start. What is that? Well, it's going to be 0.0 meters minus 6.0 meters. And we have to calculate the signs. This minus makes plus. This is plus 6 meters, just like we had before. So it looks like the displacement is the same in all coordinate systems, except not quite. There's a reason I skipped the second one, this one here. Notice the second one is different in that it points the other way, right? All those three were pointing the same direction. This one pointed a different direction, which is fine. But in this coordinate system, I start at the house, right? Because I start here, and this is the origin. Start at 0.0 meters, plus or minus doesn't matter because it's 0. And I end, well, I end at the car, that's 6 meters over here, but that's in the opposite direction of where this ruler points, so I'm at minus 6. I end up at minus 6 meters. And then the displacement, the change in position, will have been, well, x end minus x start, which is minus 6 meters minus 0 meters, which comes to minus 6 meters. So this is different. The answer here is minus. The answer for all of those displacements was plus. It's still 6, right? It's really just a distance. But it's in the, we've moved in the direction for 1, 3, and 4 that was in the same direction that the axes point. They point to the right, we moved to the right. Doesn't matter where the origin was, we moved in the same direction as the axis. In this case here, for coordinate system 2, our motion was in the opposite direction of the direction that the axis is pointing, and so that's where we get this minus sign from that pops into our final answer for the displacement. Okay, let's just stick with the scenario for just another second. So let's imagine this following situation. I've got the same picture at the top. But I imagine, well, what if I leave the house, leave my front door, and I walk around a tree, and then I walk to my car? What's my displacement then? So, it doesn't matter what coordinate system you pick. I'm just going to stick with one now. I'm going to pick the blue one because I like it. But, you know, any of them would work just fine. The displacement is still, where do you end up? What's your final position? Minus where did you start? Your initial position. Doesn't matter how you got there. So it is still, oops, you end at, 11 meters. You start at 5 meters, right? That's the position in the blue coordinate system of the front door. So that is still 6 meters, just as before. It doesn't matter how you got there. Doesn't matter how you got there. Now, you could have split up the calculation into 2 chunks. That would be an option. Let me just draw this picture again. Here's my house, right? Going here to the tree, right? Going from here to here in the blue coordinate system, that would have been going from position 5 to position 0. This would be delta x equals this would be delta x1, now referring to like the first part of the trip, right? So I'm not putting a circle around it. It's all in the blue coordinate system, all in coordinate system 1, but it's the first part of the trip. So I'm calling it delta x subscript 1. That would be minus 5. We start at 5, I end at 0. And then for the second part, so my car's going to be over here. I want to go from here to here would be a displacement of plus 11 meters. Would be delta x2, right? The second part of the journey. And then my total displacement is just the sum of the 2. At minus 5 plus 11, well, it's still plus 6, same as before. So it's all consistent, right? So I can split this journey up into more than one chunk, and we're going to end up with the same total displacement. What's different, though, is the distance traveled, right? So different distance traveled. Like if you drove 5 miles one way and then 11 miles the other way, your displacement would be 6 miles. But the odometer in your car didn't go up by 6 miles, it went up by 5 plus 11, 16 miles, right? And you used up fuel for 16 miles of driving, not for 6. You don't get fuel back because you're going in a negative direction in the coordinate system. Right? So often the distance traveled matters. So here, the distance traveled is going to be 16 meters, 5 plus 11. Whereas if you had taken the direct route, it would have just been 6 meters. So you would never have gone those 5 meters there and then the 5 meters back to the house before we kept going. So don't confuse the two. Displacement versus distance traveled. Interestingly, the distance traveled doesn't really depend on your coordinate system at all. Right? Displacement, the sign sort of dependent on it. When we go to more than one dimension, it's going to be a little bit more complicated still. But the distance traveled, that is literally the thing that your car's gonna tell you as counting up your miles. Alright, now for the final bit of this lecture, let's just very quickly have a look what happens if we have to use more than one ruler to describe position. So let's look at a 2D example. 3D examples are hard to draw because the paper is inherently two-dimensional, right? I can't sort of draw coming out of the paper very easily. You can sort of try it, but it's hard to do accurately and precisely. So let's imagine this is a view from above. The flower isn't drawn from above, but you get the idea. And the tree drawn from above here, we're just looking down on the leaves. And I'm going to make the center of the tree right here. That's my reference point. Flower, I'm just going to pick the bottom bit here. So I want to know what's the position of the flower if my coordinate system is centered at a tree. The tree is my origin. So I need coordinate axes. And in this case, it's not as does the axis point right or left. I mean, it could point any direction, right? Things could be there or there or there. Like one single ruler is just not going to tell me where things are because not everything is along a single line. So I can define a coordinate system and I might do it like this. I might say, okay, this direction is one ruler, and then I'm going to have a different ruler in this direction. And let me call those X and Y. I could make other choices, but these are the most common ones, sort of a convention. In 95% of all problems, you're going to see X and Y. So these are my coordinate axes. So now the position of the flower is, well, you can imagine it like this. Imagine those here, they form a kind of grid, right? So it's sort of like anywhere, everything along this line here is at position x equals 1. Everything along this line here is at the position x equals, I know, 0.1, 0.2. So the flower is going to be essentially at a position where I can see, well, how far, say, east is it of the tree? Oh, 2 meters, right? So I've shown here. How far north is it of the tree? 1.5. So I might say x of the flower would be 2.0 meters, because x is the axis that points right, that shows me the, in this case, positions in a west-east direction. West would be negative, east would be positive. And in the y direction, it would be at 1.5, and again it's in the same direction that my axis is pointing, so it would be positive 1.5. So 1.5 meters. So this together, that is the position of the flower. It's not a single number, it's two numbers. So, so together give the direction of the flower. Sorry, not the direction, the position, excuse me. Going nuts. Position of the flower, right? And we call this a vector. Let's define this term. A vector has a magnitude, kind of how far is it, and a direction. And one way to express this is in terms of its components. So magnitude plus direction. And here this has been expressed in what's called component form, meaning x equals y equals and so on. Right? So you mean by component form. You could also express it literally as a magnitude and a direction. Magnitude meaning how big is it, right? So another way to denote this would be to say, well, how far is the flower from the tree? Let's call, so the position is the vector. We're going to talk about vectors more in a little bit in one of the follow-up lectures. But I might write this this vector as x with a bar on top, with a little arrow on top, and that means this quantity is a vector. So this would be essentially x and y together, which I can write in this sort of one above the other with big parentheses around them. It's just a way of noting down kind of the single position where the flower is, but to express it I need two quantities. I need x and I need y. Another way I could have done this is the magnitude. The magnitude is literally the distance, and I would write this as the kind of absolute value, right? 2 bars, absolute value of the vector. This notation. So it's kind of the straight line distance. Straight line length of the position vector from here to here. We'll talk about vectors more later, as I said. So in distance, which would be, well, what is the straight line distance? It's not 2 plus 1.5, right? If you want to find what this distance here is, oops, should be a straight line, I need the Pythagorean theorem. This is a right angle triangle, because the two axes, for our purposes, have to be at right angles. Otherwise, things get very complicated. So, right angle triangle, right? So the length of this distance here is x squared plus y squared, take the square root. So it's going to be x squared plus y squared, the x position plus the y position, take the square root. It should be 2 meters squared plus 1.5 squared. Now we can do the math here. It's 4 plus 2.25, that's 6.25, which comes to exactly 2.5 meters, right? So that is the distance from here to here, 2.5 meters. And then for the direction, I can define an angle. Tend to call angles very often theta, or just like lowercase Greek letters. For some reason, physicists really like to use theta as the first sort of symbol for an angle when an angle comes up. It's just a strange physics thing, I suppose. You can give it called alpha, beta, whatever Greek letters you can come up with. Theta is a very common one to use, no particular reason, except kind of what we do. Which angle? Well, maybe this one here. Theta. Well, what's this? Okay, now we need to use trigonometry. So it's right angle triangle, so you could say sine of theta is opposite over hypotenuse, or some other combination. I'm going to use maybe the tan, opposite over adjacent. If you feel a bit rusty on your trick, you really need to review that. We're going to need it a lot. Well, how do I find this? You just put a colon here right now. Got the tan theta is equal to, opposite is 1.5 over adjacent of this angle here, that's 2. So that is 3/4, 1.5 over 2, and so that makes, I'm going to squeeze it in here, that makes theta equal to 36.5 36.87 degrees, I think. You want to check it with your own calculator. So Pythagorean theorem here to determine the actual distance, and then the angle I determine essentially from trigonometry, and I could have used sine instead, opposite over hypotenuse, because I calculate the hypotenuse, or cosine, adjacent over hypotenuse. Either way, it's going to get me to the same answer. You want to make sure you're on top of those things. We're going to do a little vector review session in a little bit where we go through some more examples. But you're going to need vectors in the context of displacement, in the context of velocities, accelerations, and so on. It's going to be very important. So maybe now is the time to get started reviewing those trick concepts. Now, strictly speaking, I want to say, well, what angle that is. So I might call this angle here, because it's the angle between the east direction and the actual direction that the position of the flower is. I might call this 36.87 degrees north of east, because off east you have to turn north. So if you see this notation, that's what it means. I could have expressed it as an angle east of north. Then I would have talked about this angle here. It's all consistent. There's more than one way of doing it. Alright, so we've got the basics down of how to describe position displacements, and that's what we're going to need to then talk about how fast things are moving. We've understood what frames of reference are, and we're going to put all of this into action in what's going to come next. Thanks for watching.